Top 10 gemstones that came from Earth's deepest places. The surface of Earth has been mapped, mined, and measured, but more than 90% of the planet remains physically unreachable. Beneath the crust lies a world of heat, pressure, and unknown architecture, where minerals behave differently from how they do in daylight, and time moves at the speed of tectonics. Yet a few crystals have managed to escape. Some were formed dozens of kilometers below the surface, others hundreds, and brought up not by machines or drilling, but by forces that remain only partially understood. Magma bursts, mantle plumes, and ancient subduction zones. These are not common gemstones. They are mineral records, unchanged since formation, unaffected by erosion, and untouched by human fabrication. And the deeper they form, the more precise their story becomes. This is a journey through the most precious gemstones ever discovered, and each one tells us something the surface never could. Don't forget to press and hold that like button, leave a comment, and hit subscribe before we begin. Ranked 10th, Spessartine Garnet, the flame born below ancient continents. Not every gemstone is born in chaos. Some emerge from stillness, where nothing moves fast and nothing interrupts. Spessartine Garnet belongs to the second category. It forms deep within the most stable parts of Earth's crust, in geological settings that have remained quiet for hundreds of millions of years. Beneath the cratonic shields of Nigeria, Madagascar, and Namibia, spessartine crystals develop slowly, locked inside pegmatitic veins that cut through ancient continental rock. At depths of 25 to 35 kilometers, far from fault lines or volcanic systems, time becomes the only active force. Mineralogically, spessartine is a manganese-rich garnet. Its vivid orange to reddish tones are not cosmetic. They result from precise chemical conditions rarely found outside these ancient terrains. High temperatures, moderate pressures, and manganese-enriched fluids are required, and those conditions only persist beneath continental interiors that haven't shifted in eons. These aren't the zones of mountain building or subduction. They're continental cores, geologically quiet but chemically complex. In scientific terms, spessartine is more than a gemstone. It's a geochronological marker. Its presence tells geologists where stable crust once existed and where it remains. Some crystals from the Yos Plateau in Nigeria or the Ambatondrazaka region of Madagascar date back to Precambrian tectonic events. In those regions, the surrounding rocks act as a geological time capsule, preserved, intact, and essentially unchanged since long before the appearance of vertebrate life. Commercially, spessartine is not as widely distributed as other garnets. Transparent specimens large enough to facet are rare, and often appear only in small, isolated deposits. Yet those few that do emerge carry a visual intensity unlike any other garnet species. Their bright, saturated hues are not the result of enhancement. They come directly from the geological environment in which they formed. For collectors and gemologists, spessartine serves as both a scientific artifact and a visual record of Earth's deeper, quieter processes. In the broader context of gem formation, spessartine occupies a unique place. It does not result from violent eruptions or tectonic collisions. It forms when nothing else is happening except the slow accumulation of time, heat, and chemistry beneath the world's oldest lands. Ranked 9th, tanzanite, the rift gem that exists nowhere else on Earth. There is only one place on Earth where tanzanite has ever been found, just one. A narrow strip of land at the foot of Mount Kilimanjaro, no wider than a city block and only a few kilometers long. It lies within the East African Rift, a fracture in the continent that's slowly pulling itself apart. Here, tectonic forces stretch the crust thin enough to let something rare happen. Tanzanite isn't the product of high-pressure mantle processes, nor is it a mineral that appears across continents. It's a vanishing point phenomenon, formed from a perfect storm of vanadium-rich fluids, regional metamorphism, and the geological instability of a rift zone. The mineral is a variety of zoisite. Still with a twist, when trace amounts of vanadium substitute into the crystal lattice, it transforms optically, chemically, and commercially into something entirely distinct. Scientifically, tanzanite is valuable not just for its color, but for the story its formation tells. It documents a moment in time when East Africa began to split apart, when crustal extension, metamorphism, and fluid activity intersected in one location, never repeated elsewhere. That alone makes it a case study in geological specificity. No other gem captures a rift event so precisely. From a historical standpoint, tanzanite entered the global gem market late. It was discovered in 1967 by a Maasai herder named Ali Juyawatu and quickly brought to the attention of international dealers. But the story didn't unfold like most gemstone rushes. By the 1980s, the area had already been locked down. Tanzanian authorities imposed strict mining regulations, military oversight, and heavy taxation. The reason was simple. Tanzanite was a finite resource, and everyone knew it. By the early 2000s, the gem had become synonymous with controlled scarcity. Unlike emeralds or sapphires, tanzanite had no alternate sources, no backup deposits, no offshore discoveries. That created both opportunity and conflict. Smuggling rings emerged. Mines collapsed. Foreign companies were pushed out. What remained was a state-controlled system guarding a resource whose geological origin could not be replicated. In gemological terms, tanzanite's pleochroism, its ability to show blue, violet, and burgundy hues, depending on the viewing angle, is often emphasized. But behind the color is a truth more important. This is a gem born from a tectonic wound, unique to a specific time and place. When the rift closes or expands and the crust moves on, tanzanite formation comes to an end. Not because the material runs out, but because the conditions that created it disappear forever. Ranked 8th, chrome diopside, the emerald flash from the mantle's edge. In the frozen reaches of Siberia, beneath layers of permafrost and volcanic basalt, lies a mineral that rarely surfaces. Chrome diopside is not rare because it's impossible to form. It's rare because the geological window that lets it reach the surface is narrow and closing. Geologically, chrome diopside is a calcium-magnesium silicate, a pyroxene mineral with a formula. But what gives it its electric green color isn't part of the base chemistry. It's chromium, introduced during crystallization inside ultramafic mantle-derived rocks. That small trace element, paired with extremely high temperatures and modest pressures near the crust-mantle boundary, gives chrome diopside its unmistakable hue. Most of the world's gem-grade material comes from just one region, the Inegli deposit in eastern Siberia. Here, volcanic pipes called kimberlites cut deep into the earth and transport minerals upward, sometimes from depths of over 100 kilometers. Chrome diopside often rides along with these eruptions, alongside garnet, olivine, and sometimes even diamond. But unlike diamond, chrome diopside is fragile. It cleaves easily, breaks under pressure, and reacts poorly to mechanical stress. That's why you won't see it in high-end engagement rings. Not because it isn't beautiful, but because it doesn't survive well outside the conditions that formed it. Its geological story, however, is precise and essential. Chrome diopside helps geologists trace mantle-derived rocks and understand how chromium behaves in the deep earth. In many diamond exploration programs, its presence in surface soils is used as a pathfinder mineral, one of the first indicators that the mantle has left its fingerprints behind. Despite its scientific value, chrome diopside remains underappreciated. Its color rivals emerald. Its chemistry reflects mantle evolution, but it lacks the romance, the mythology, the commercial mystique. What it offers instead is clarity, both optical and geological. It shows where the earth was once fluid, molten, and in a state of constant transition. And it reminds us how close the crust can come to losing the minerals it barely knows how to bring up. Ranked 7th, kyanite, the blade forged in subduction zones. Every mineral forms under rules defined by pressure, temperature, and time. But kyanite obeys one of the strictest rules in the entire mineral kingdom. It forms only in narrow bands of the earth where pressure outruns heat, where rocks are buried faster than they can warm. Where two tectonic plates collide, one is forced deep beneath the other. Kyanite is an aluminum silicate and belongs to a group of minerals known for polymorphism. Under the right conditions, the same chemical formula can produce three completely different structures: andesite, sillimanite, or kyanite. Of these, kyanite forms under the highest pressure. Its long, bladed crystals mark one thing: a rock that has survived a deep burial event, often 50 to 100 kilometers beneath the surface. Kyanite crystallizes in solid-state conditions. It doesn't need magma. It doesn't need volcanic activity. It requires slow, relentless compression. That's why it appears in subduction zones, places where one tectonic plate slides beneath another, carrying sedimentary and crustal rocks down into the mantle's edge. Over millions of years, those rocks have undergone significant changes. The original minerals break down, and kyanite grows in their place. Its crystals are anisotropic, optically variable depending on angle, and its hardness varies by axis, making it difficult to cut or set. Yet its formation leaves a record that geologists can read with precision. Kyanite-bearing rocks are found in the Himalayas, the Alps, the Scottish Highlands, and the collision belts of South America, all areas shaped by plate convergence. Each occurrence marks a zone where crustal material was once pushed deep into Earth's interior before being exhumed. To a mineralogist, kyanite is more than just a gem. It's a phase diagram brought to life. It proves that the rocks around it were once buried far below the surface, and that they returned, intact, transformed, and chemically rebalanced. Its color, typically blue but sometimes green or even gray, is not the reason it's valuable. Its value lies in what it proves, that pressure can change structure without changing composition, that deep earth processes are not always violent, but deliberate, and that some minerals form not from what is added, but from what is endured. Ranked 6th, blue sapphire, the royal gem with subterranean origins. Long before it adorned crowns, relics, or religious artifacts, blue sapphire existed where royalty could not reach, inside the earth, where pressure rewrites mineral structures and heat unlocks chemical order. Its story begins deep within metamorphic terrains, zones where crustal rocks are caught in the collision between tectonic plates. Not in the fire of volcanoes, but in the compression of time and temperature. Geologically, sapphire is a variety of corundum. Its iconic blue color isn't part of its core formula. It originates from trace amounts of iron and titanium, which are introduced during the crystal formation process. But achieving that balance isn't easy. Corundum needs an aluminum-rich, silica-poor environment. The presence of iron must be exact, not too much, not too little, and the pressure must be sustained long enough for complete crystallization to occur. These conditions exist only in specific metamorphic environments, such as those found in Sri Lanka, Kashmir, and Madagascar, where crustal rocks were buried, altered, and eventually exhumed after hundreds of millions of years. Blue sapphires often form in what geologists call metasedimentary marbles, or high-grade gneisses, rocks that have undergone multiple phases of regional metamorphism. In some cases, they survive not just one tectonic cycle, but two or more tectonic cycles. They are quite literally survivors of deep earth dynamics, carried upward through slow uplift and erosion rather than sudden eruption. Historically, few gemstones have carried as much symbolic weight. In medieval Europe, sapphires were believed to represent divine favor. In ancient Persia, it was believed that they reflected the color of the sky itself. Yet none of those cultures knew the truth, that each sapphire had endured geologic forces more ancient than the civilizations that later revered them. Some of the finest specimens, such as those from the legendary Kashmir mines, likely formed during Himalayan orogenic events. Others, like those from Sri Lanka, are older still, tied to Precambrian metamorphism in a crust that hasn't moved significantly in nearly 1 billion years. The rarity of blue sapphire is not about supply, it's about formation. The deep earth doesn't easily allow corundum to exist. Most aluminum-rich rocks contain too much silica, which redirects the chemistry toward feldspar or sillimanite. Only in localized zones, rich in aluminum, poor in quartz, with the right fluid interactions, can sapphire emerge. And even then, only a fraction achieve the optical clarity, the chromatic balance, and the structural integrity required to become gemstones. In the end, sapphire's real value lies not in color, weight, or fame, but in its survival. It was formed not by chance, but by precise constraint. And when brought to the surface, It remains a geological signature of the deep metamorphic past. Ranked 5th, pyrope garnet, the mantle messenger in blood red. Not all garnets come from the crust. Some are born deeper, far below the granite continents and sedimentary layers, inside the Earth's upper mantle, where silicate minerals take on new forms under immense pressure. Pyrope is one of them. Pyrope is a magnesium-aluminum garnet. Unlike its crustal counterparts, it forms between 80 and 150 kilometers below the surface, within peridotite and eclogite, rocks native to the mantle itself. These conditions are not rare in the deep earth, but access to them is. Most of the time, what forms down there stays there. Pyrope is different. It sometimes rides the same violent geological elevator that carries diamonds, the kimberlite eruption. Kimberlite pipes are fast-moving volcanic conduits, formed in hours or days, that blast deep mantle material to the surface. Diamonds can survive the ride because they're hard. Pyrope survives because it's stable. As a result, it has become one of the most essential tools in modern mineral exploration. In regions like South Africa, Siberia, and Western Australia, geologists have used pyrope garnet as a tracer mineral, a signal that mantle-derived rocks have reached the surface. Its chemistry tells a precise story. Variants rich in chromium or calcium indicate specific mantle environments, and those with certain trace element ratios are statistically associated with diamond-bearing zones. Before most diamond mines are ever drilled, pyrope is what points the way. Visually, it differs from other garnets by its deep red coloration, often with a slight violet or brown undertone. But the color is not what defines its value. What matters is context. A pyrope crystal on its own is a curiosity. A pyrope crystal surrounded by specific spinel, ilmenite, or chromite compositions can trigger the next phase of a multi-million-dollar exploration program. Scientifically, pyrope is also a key to understanding mantle composition. Studies of its inclusions have revealed fluid histories, subduction residues, and even trace evidence of ancient oceanic crust dragged deep into the earth. Yet most of these garnets, like the diamonds they sometimes accompany, never reach the surface. Those that do arrive are encapsulated in xenoliths, scattered across old volcanic fields, or trapped inside permafrost after eons of erosion. In that sense, pyrope garnet functions less like a gemstone and more like a geological witness, one that confirms a direct connection between the surface and the depths from which few minerals ever return. Ranked 4th, peridot, the green gem thrown from the mantle. Few gemstones reveal their origin with such clarity. Peridot doesn't hint, it declares, this came from below. Mineralogically, peridot is the gem-quality variety of olivine, a magnesium-iron silicate. It forms deep within the Earth's upper mantle, typically at depths of 80 to 150 kilometers, where high temperatures and specific chemical conditions allow olivine crystals to grow in ultramafic rocks, such as peridotite. Under most conditions, these crystals remain locked underground and are unreachable. But on rare occasions, they rise to the surface, carried upward in pulses of magma. Peridot is more tolerant. It travels within basaltic lava, often erupting through shield volcanoes or fissure systems. In regions such as the San Carlos Apache Reservation in Arizona or the Himalayan foothills of Pakistan, peridot reaches the surface embedded in lava flows or trapped within xenoliths, fragments of mantle rock torn loose and expelled during volcanic eruptions. What makes peridot scientifically compelling is not just its origin, but its consistency. It's one of the few gemstones that can be confidently traced back to mantle depth without ambiguity. Its formation requires neither metamorphism nor surface chemistry. It does not recycle crustal material. It begins and ends below. In some rare cases, peridot has also been found in palisite meteorites, iron-rich space rocks formed during the early history of our solar system. These extraterrestrial samples contain olivine crystals, nearly identical in composition to terrestrial peridot. The difference lies not in chemistry, but in setting. One formed inside Earth, the other inside a shattered protoplanet. From a visual standpoint, peridot is easily recognized by its yellowish-green hue, high birefringence, and lack of pleochroism. Its color does not vary with angle or lighting. It is stable, definitive, and tied directly to the iron content in the crystal. Too much iron and the color dulls. Too little and it shifts toward yellow. The precise balance determines not only beauty, but also the depth of origin. Geologically, peridot is also used as a window into mantle processes. Studies of olivine inclusions have revealed clues about the thermal gradients, fluid dynamics, and melting behaviors of the Earth's interior. It's not just a gemstone, it's a mantle probe, one that reached the surface not by intention, but by force. Ranked third, Grandidierite, the sea-colored gem, born in a submerged continent. Some minerals are defined by the environments that shape them. Others are grouped by the continent to which they belong. Grandidierite belongs to neither. It is characterized by geological isolation. First discovered in 1902 along the southern coast of Madagascar, Grandidierite was initially considered a scientific curiosity. The crystals were opaque, embedded in rock that showed signs of extreme metamorphism. No jewelry was cut. No market followed. For nearly a century, the mineral remained unknown outside mineralogical literature. Its geology is precise. Grandidierite forms in boron-rich, magnesium-bearing environments that undergo high-grade regional metamorphism. It requires both high temperature and pressure, but only under conditions where fluid chemistry is tightly constrained. Conditions that rarely occur together and rarely last long. The result is a gem that forms only in specific rocks, often aluminous pegmatites, sometimes hornfells, always with a metamorphic overprint. For most of the 20th century, only a few small specimens existed. Then, in the early 2000s, a new deposit was uncovered, again in southern Madagascar, near the cliffs of Tranamaro. This time the material was transparent. It could be cut. And suddenly, Grandidierite had moved from lab catalogs to international auction houses. Its color is complex, a layered mix of green, blue, and teal that shifts depending on the crystal's orientation. This isn't color zoning or treatment, it's pleochroism. The mineral's crystal structure bends light differently along each axis, making a single gem appear to shift between hues as it moves. In gemological terms, few minerals behave like it. Fewer still survive the cutting process with that behavior intact, but its origin remains the most defining factor. Madagascar is not just an island. Geologically, it's a fragment of an ancient continent, Gondwana, split apart over 150 million years ago. The rocks hosting Grandidierite are part of this story. They preserve metamorphic events that no longer exist on the active Earth, frozen in formations older than most modern mountain ranges. Grandidierite has not been found in multiple countries. It's not associated with modern tectonic belts, nor does it appear in recent volcanic terrain. Its presence is strictly regional, a product of a deep, ancient process and a geography that broke away from the rest of the world long before humans arrived. Today, Grandidierite remains among the most compositionally stable and optically rare gemstones known to science. Yet every facet cut from it is a byproduct of chance. The right chemistry, the right tectonics, the right erosion cycle. Once, in one place, then buried again under the weight of time. Ranked second, diamond, the indestructible crystal from Earth's mantle. Diamond is not rare, but deep diamonds are. Most gem-quality diamonds form between 140 and 200 kilometers beneath the Earth's surface, at the base of ancient cratons where high pressure and moderate temperatures coexist for millions of years. At these depths, carbon becomes unstable in its usual forms. Given enough time and the absence of oxygen, it crystallizes into something else entirely. A cubic lattice of carbon atoms, tightly bound, nearly incompressible. Diamond. But some diamonds form even deeper, beyond the lithospheric mantle, within Earth's transition zone. Here, between 410 and 660 kilometers down, the mineral landscape undergoes a change. Olivine transforms into wadsleyite, pyroxenes lose stability, and fluids, when they exist, carry signatures from subducted oceanic crust. It's in this environment that super-deep diamonds form, and what they bring to the surface has changed how geologists understand the planet's interior. Diamond survives extreme transport. Kimberlite eruptions, rare, gas-charged, and violently fast, carry them upward in under 24 hours. If the ascent is slower, the diamond reverts to graphite. If the temperature is too high, it oxidizes. If the pressure is lost too soon, it fractures. Every diamond that survives to reach the surface is, in geological terms, an exception. Some of these diamonds contain inclusions, minerals trapped inside during growth. They aren't flaws, they are records. In 2014, one such inclusion was identified as ringwoodite, a high-pressure form of olivine that is stable only between 520 and 660 kilometers in depth. It contained hydroxide ions, evidence that water exists deep within the Earth's mantle. Another contained calcium silicate perovskite, later reclassified as bridgmanite, the most abundant mineral on Earth, but unstable at surface pressure. Only diamond could have preserved it long enough to be studied. From Siberia to Botswana to Canada, deep origin diamonds now provide complex data about the planet's inaccessible interior. They reveal recycled ocean crust, mantle transition zone chemistry, and the survival of volatile elements under crushing pressure. Their value lies not in sparkle, but in signal. These are not decorative stones. They are thermodynamic outcomes, crystals that only exist because of specific conditions, temperature, pressure, redox balance, and time, align once far below what humans will ever drill. In first place, bridgmanite, the deepest mineral ever discovered. Beneath the crust, beneath the mantle's upper layers, and even beneath the zone where diamonds form, lies a layer of Earth that defines the planet's structure more than any other, the lower mantle. Pressures exceed 23 gigapascals. Temperatures pass 2,000 degrees Celsius. Here, the atomic architecture of minerals begins to collapse and then reorganize. In this environment, bridgmanite forms. Bridgmanite is a high-pressure silicate with the formula magnesium iron silicate. Structurally, it adopts a perovskite-type lattice, a dense, compact form that can only exist at depths between 660 and 2,700 kilometers. It is, by volume, the most abundant mineral on Earth, and for decades it remained entirely theoretical. Its name honors physicist Percy Bridgman, whose work in high-pressure physics helped establish the rules under which it could form. But the mineral itself wasn't confirmed until 2014, when a slight inclusion, trapped inside a super-deep diamond from Guiana, Brazil, was recovered and analyzed. For the first time, bridgmanite was observed not in the lab, but in nature. It cannot survive at the surface. The moment it rises above transition zone pressure, it reverts to its original state. Its lattice collapses. The mineral transforms into lower pressure phases, such as in statite or glass. That's why all known specimens exist only as inclusions. Preserved inside diamonds form far deeper than conventional gem material. Bridgmanite doesn't occur in jewelry. It cannot be cut. It cannot be set. Its only purpose is structural. It carries the weight of continents. It transmits seismic energy across the mantle. It controls convection, thermal gradients, and the physical behavior of Earth's interior. And yet, it is invisible. There are no mines, no markets, no visual catalogs. All data comes from seismic modeling, laboratory synthesis, and nanometer-scale inclusions. Bridgmanite is not a gemstone in the traditional sense. It is the crystalline infrastructure of the planet, the phase that holds up everything else. Its presence at the top of this list is not about value. It is about proximity to truth. Among all minerals brought to the surface, none come from deeper. None come with more structural consequences, and none are less accessible by human means. In the hierarchy of Earth's materials, bridgmanite is not the rarest. It is not the brightest. It is the foundation. The gems on this list weren't chosen for beauty. They were chosen for depth. Each one formed in silence, far beneath oceans, cities, and tectonic plates. Some passed through fire, others through time. All of them emerged carrying signals from regions humans will never reach. In a world obsessed with the surface, they remind us of the structure underneath, of the mantle that moves continents, of the minerals that hold the planet together. Most people will never hold these stones, but understanding where they come from, that brings us closer to the Earth than any mine ever could. The deeper the origin, the more apparent the evidence, and we've only just begun to read it. Let us know which one resonates with you in the comments, and don't forget to like and subscribe to our channel for more content like this.